All right, this is Honors Algebra 2 Pre-Calculus. We're doing 12.4 in Algebra 2, which is measures of dispersion. So we've learned about the measures of central tendency, meaning the mean, median, and mode for a data set. These are all methods to find something akin to an average value of the set. Sometimes averages don't tell the whole story, though. Two data sets can have very similar measures of central tendency, but look incredibly different. And so I'm going to walk you through an example in just a second. It says here's an example, and it's going to be on the next slide, because I realized after I made this slide that I couldn't fit it here. So in this section, we're going to learn about what's called measures of dispersion, which are methods to describe how the spread out values in a data set are, or how what the spread of a set is. So you've learned two of these already. You learned range, which is max minus min, and you learned the IQR, or interquartile range, which is Q3 minus Q1. In this section, we're going to start by learning another measure of dispersion, mean deviation, and then we'll talk about variance and standard deviation as well. So here's an example of two data sets that have the same measures of central tendency, literally exactly the same, but incredibly different look, right? So I gave you 5 values. I gave you 1, 98, 100, 102, and 199. The mean of this set is 100. There's no mode, and the median is also 100. You can see that this other data set, the red one that I gave you, the 90, 95, 100, 105, 110, also has an average of 100, also has no mode, and also has a median of 10 or of 100 rather. But notice that that's where all of the comparisons end. If you look at these as a box and whiskers, you can see that the blue data is incredibly spread out. The red data is very condensed. You can see that the range, right, if we did maximum minus minimum, we get a very big range for the blue data set and a very small range for the red data set. We get a very large interquartile range for the blue set and a very small one for the red set. So the way that data is spread out is also significant. Things like mean, median, and mode are very useful, but they only tell part of the story. So let's talk about mean deviation. It's going to have a notation that you find a little bit off-putting at first. I promise I'm going to walk you through how this notation works, and then you're really not going to have to stress about the notation now. We're going to revisit this notation with this sigma when we get to chapter 9 of pre-calculus. So don't panic if the notation seems daunting. I promise the actual concept isn't that bad. So mean deviation of the data set x1, x2, x3, etc., up to xn is the mean of the absolute values of the differences between the data values and the mean, which is x with that line over it, right? That's the mean. So the way that that's written is 1 over n, a sigma from I is 1 to n, and then the absolute value of x sub I minus the mean. Okay, this looks incredibly daunting. So sigma should look more like this, right? But my sigma usually looks more like this because I'm lazy and it's easy. But for those of you that are neat people and write things well, technically the top and bottom line should be closer to parallel, and there's sort of like a little serif there. Honestly, it's just not a level of commitment that I'm willing to put in. This is a capital sigma. Later in this video, we're going to run into lowercase sigma. So these are Greek letters. This is a capital sigma. Capital sigma means sum. It means add in math. It's going to come up. You'll see it a lot. Sigma means sum. So when you see it sigma, essentially this is a way of condensing a list of sums, a bunch of sums of things that are being added together into one small notation. And it means you're going to have a bunch of these values, add them all up. So the way we do this, so that this letter I, and you can see that in purple, is called the index of summation. See how there's an I here and an I here? It's not the I as in the square root of -1. It could be a J or a K. It could be any letter. It's often I for index. And where we start with that I is right here at this lower bound of 1, which I highlighted here. Where we stop is at this upper bound of n, which in the problem is going to be a number. Now, eventually you'll get to math where it's going to keep being an n, and you're going to have to deal with that. But in all the problems you're going to see now, it's just a number. It's going to be a 3 or a 5. So what this is basically saying is, if we were to write this out, so let me just show you what this would look like. Let's say I wanted to find the first 3 sets. I might have actually done this. Hey, never mind. I did it on the next page. Let's go to the next page. So here's what this would look like if I picked 3 pieces of data, okay? I would start at the first piece of data, 1. I would end at 3 because there's 3 pieces of data. And what would happen is I would say that this is, instead of 1 over n, it would be 1 over 3 because n is 3, right? So 3 pieces of data would mean n is 3, right? I start with x sub 1 minus the mean, right? And then I say plus because sigma means add, right? So plus. And then I do x sub 2 because 2 is the next number after 1 minus the mean. And then I do plus because sigma means add. And then I do x x sub 3, which is the last one I do because, see, I'm supposed to stop at 3, minus the mean. So essentially what I'm doing is I'm finding the difference between the mean and the x values in the list. Like this is saying my data list is this. These are my 3 values in my list. I'm finding the difference between the mean, right? This is the mean, and the data value, right? And then this 1/3 is because I'm supposed to be finding the mean of the differences. So this is 1, 2, 3 of these absolute values, and I'm finding the average of them by dividing by 3. That's all this means. So why would you use sigma notation? Well, if you don't have 3 data points, if you have 100 data points, you can see that it takes a really long time to write them out. Sigma is a really succinct and clear way to write this information. It doesn't take as much time, and we're also going to learn shortcuts about how to deal with sigma later, just not yet, okay? So again, with sigma, writing 3 data points is the exact same amount of work and space as writing it for 100 or 1,000,000 or 100 million. It wouldn't matter. So let's try this so it seems less daunting. The first thing we're going to have to do is find the mean. So I'm going to go ahead and list my data points here because I know I'm going to need the data points, right? So my first one, x1, x2, x3, x4, x5, right? So these are my data points, right? And I have extra rows because I use the same column for things, so we don't need that. I need to find the mean. So remember, we can use one expression for the mean is to use the x with that line over it, and that way you don't have to write mean. So it's going to be 1 plus 4 plus 6 plus 8 plus 11 all over the 5 terms I have, right? So I think that that's 30, right? Because this would be 5 and 6 is 11, 19. Yep, so that's a 30 over 5. So the mean is 6. Okay, so now the mean is 6, and that mean is always 6. I just put a column so it's easier. So the absolute value, deviation, right? Deviation is how far this number is from this number. You can either do it as absolute value of 1 minus 6 and then actually take the absolute value of -5 and get a 5. Or you can just say in your head, how far apart are 1 and 6? Oh, they're 5 units apart, right? If you can just in your head say, oh, 4 and 6, that's 2 units apart. 6 and 6 is no units apart. 8 and 6 is 2 units apart, and 11 and 6 is 5 units apart. That's fine. If you need the thing where you get that this is the absolute value of 4 minus 6, and this is the absolute value of 6 minus 6, which is 0, and this is the absolute value of 8 minus 6, which is 2, that's fine. If you don't need it, that's also fine. So these are my deviations, right? So the mean deviation is literally the mean of the deviations. So the mean deviation means find the mean of these numbers. So 5 plus 2 plus 0 plus 2 plus 5 divided by 5. Well, I think that that's a 14 divided by 5 or a 2.8. Right? So that's all this means, right? And it's a lot easier with the table. You could write this in sigma notation, but there's not a lot of reason to do it because really all sigma notation means is when you find these 5 values, add them. That's what sigma notation is saying. All right, so go ahead and give this a try. Again, I'm going to go ahead and plug these values onto our table. The first thing you're going to want to do is find the mean, right? The first thing you're going to want to do is find the mean. So I'm going to find the mean, which is that x with the line over it. It's going to be 10 plus 12 plus 13 plus 16 plus 17 plus 22 divided by the 6 numbers I have, right? And you can add this in your head. That's totally fine if you want. If you're like, hey, brain, I'm just not about to do that, that's also totally fine. So I think that I get that this is a 25 right here, right? This would be 33 and a 22. So I think that this is a 55. So I think I get 25 plus 55, which I feel is possibly an 80 over 6, but I'm not sure if my brain is right, so we're going to go ahead and check. Because my brain is tired and does stupid things sometimes. Oh, hey, it's not a 25, it's a 35. Sorry, it's a 90 over 6. I think it's a 90 over 6. My bad. Which would be a 15. Yeah, so I think it's a 90 because sometimes my brain is slow and catches on after the fact. 16, 17, 22. Hey, 90 over 6. And then you can check by dividing by 6. And hey, it's 15. Okay, so I was guessing that it wasn't going to be a fractional answer. It's not that means can't be fractional answers. They very often are, but it would be kind of mean of me to have constructed a problem that would involve that. So, cool. So again, if you want to just recognize that the deviation is the positive difference between these things, you can realize that 10 minus 15 would be a -5, but you want the positive difference. Fine. If you need to do the thing where you say, hey, it's an absolute value of -5, that's fine. Same thing, 12 minus 15 is a -3, but I want the positive difference, so it's a 3. This will be a +2 because, again, 13 minus 15 is a -2, but I want the positive difference. 16 minus 15 is a 1. We get a 2. We get a 7. So these are the deviations, and they're the thing I want to mean, right? So my mean deviation is going to be 5 plus 3 plus 2 plus 1 plus 2 plus 7 all over 6, right? That's 8 and 10 and another 10, I think. So I think this time I think I get 20. Yeah, I think I get 20 over 6, right? So 20 divided by 6 gives me a 3.3 repeating, or you could say 3.333, right? So there's my mean deviation. All right. So mean deviation is one way to measure the dispersion, right? How spread out a data is. All right, so a set of data rather is. So the variance and standard deviation are two more measures of dispersion that are commonly used in comparing and analyzing data. So let's talk about variance and standard deviation. So this little symbol that kind of looks like, I don't know, it's like sort of a weird, kind of looks like a coach's whistle actually, right? Couldn't you see like Pitzner using that as a whistle, right? It kind of looks like a whistle. So that's a lowercase sigma. Variance is called sigma squared, right? Lowercase sigma squared. And essentially, it's the same idea as mean deviation, okay? Except instead of finding the absolute value of the deviation, you're squaring the deviation, right? So you're taking whatever the deviation is that we just found, right? Except instead of doing an absolute value, so if you go back to this table, see how we did the absolute value of the deviation, here you're going to square the deviation. And then again, you're adding them all up and finding the average. So essentially, it's the average of the square of the deviations. And then standard deviation is the square root of the variance. So you have to find the variance first to get the square root of the variance. So we're going to walk through this. Again, I'm not asking you to memorize this. If you do a stats course, which you likely will either in high school or college, you'll spend a lot more time on this and the meaning behind this. But I don't want it to be completely foreign to you if you see it. So I added some stuff to the table. All right, so let's go ahead and put our data points here. 13, 16, 17, and 22, right? So let's go ahead and find the mean, right? So the mean is going to be 10 plus 12 plus 13 plus 16 plus 17 plus 22, right? And then we're going to divide by 6. I'm not sure if that's the same set I just did. Hey, it is. Never mind. We don't have to find it again. It's a 15. We already found this. It's a 15, right? Let's double check. I think I even say that I used, oh, I didn't say that I used that data, but it's fine. So 10, 12, 13, 16, 17, 22, it's the same one. Okay, so we know this is a 15, right? So we've actually already found, I could have cheated and copied most of this, right? So we found that this is a 5 and a 3 and a 2 and a 1 and a 2 and a 7, right? So if I square that deviation, right? If I square the deviation, and it doesn't matter that, like, it really doesn't matter if it was negative or positive, because either way I'm squaring it, right? I get a 25, a 9, a 4, a 1, a 4, and a 49. Okay, so the variance, right? Sigma squared is what's going to happen, that lowercase sigma squared, when I average these, right? So I'm going to basically find the mean of the deviation squared. So 25 plus 9 plus 4 plus 1 plus 4 plus 49, all divided by 6. So let's go ahead and do that. So 25 plus 9 plus 4 plus 1 plus 4 plus 49, right? Divided by 6, right? I'm going to go ahead and store that as alpha A just in case I need it. So I'm going to say, cool, so my variance, right? So lowercase sigma squared, which it should look more like a whistle and less like a 6, but you know, lowercase sigma squared is approximately a 15.333, or if you want to be exact, it's a 15.3 repeating, because that is exact, right? So that's called variance. And then the standard deviation is what happens if you square root that. So standard deviation, which we would just call lowercase sigma, which kind of looks like a whistle, right, is just going to be the square root of that. So I'm going to do second root of the thing I called A, and I get, now that one's definitely approximate because I'm definitely rounding. And that's my standard deviation, right? So that's the idea. Now, it's easier when you have the tables, obviously, but I didn't want us to spend a ton of time making these tables. So I think we're back to using the first data set, so I actually think that we already did this work, so I'm going to be a little bit lazy, right, and just notice, oh, I guess I can just copy that the mean is 6. So the mean is 6, and then we already did the work. We don't have to start from scratch. I think I did that on purpose because these videos can be long if I make you do everything from scratch. This is a 5, a 2, a 0, a 2, and a 5, right? So we get 25, 4, 0, 4, and 25. Right, so I'm pretty sure that's a 58 if I add it together, right? So if I want to find the mean of this, right, so my variance is going to be this lowercase sigma squared. And that's going to be the sum of this, which would be the 25 and 25 is a 50, and the 4 and 4 is an 8, so 58 divided by 5. If I divide it by 10, it would be a 5.8. So if I double it, instead of being a 12, it should be like an 11.6. I don't know. Let's find out. 58 divided by 5. Hey, there we have it. So that's an 11.6. I didn't have to round. And then my standard deviation is going to be the square root of that, right? So my standard deviation is going to be that lowercase sigma, which is just going to be the square root of 11.6. So we'll square root 11.6. And we get that it's approximately 3.405 or 6, depending if I round or truncate. Okay? And there's our values. And that is it for this video.